A little pre-cal review. We know that if we have our function, y equals 2x minus 6, and by the way, the slope on that would be 2. Let's find the inverse. How do we do that? Switch the x and the y and solve for the new y. And we can see the slope on this is 1/2. Now, do you notice a relationship? The slope on the function is 2. The slope on the inverse is 1/2. Now, I used a very simple example, linear ones. Let's go to something a little more complicated, but I'm sure you can see the connection. If I take y equals x squared plus 1, we know what this function looks like, and dy dx is 2x. Our function is not 1 to 1. If we restrict the domain to 0 to infinity, my function would be 1 to 1, and therefore its inverse would also be a function. Notice that with my domain restricted from 0 to infinity, it also means my range is restricted from 1 to infinity. Now let's find our derivative at 310. I only need the x-coordinate, so the derivative at the point 310 is 6. Now let's see what happens on the inverse. First of all, finding our inverse is very simple. And taking the square root of both sides gives us plus or minus. We have restricted our domain for x to be 0 to infinity. That means our domain on the inverse takes on y's properties. So whatever happened with y on the function becomes our domain on the inverse. And our domain on the original function becomes our range on the inverse. All the properties switch. And now, on the inverse, the point that was 310 on our function becomes the point 10.3. So let's find the derivative at 10.3. Again, I'm going to take the positive part of my parabola, and we know how to take the derivative of that. Here's our derivative at the point 10.3 gives me, what do you expect it to be? Well, our first example showed that they were reciprocals, so I expect it to be reciprocal, and it is. So, important fact, xy on f becomes yx on the inverse, and the derivative of an inverse is 1 over the derivative of the function, and this is the critical part. At sum BA on the inverse. The AB is on the function, it is BA on the inverse. Is 1 over the derivative on our function, which was at AB. Now, we need a little more clarity than this. You might want to pause and write these notes down. And again, pause and write these notes down. I'll talk about this in class. Now it is important to know how to work with inverse functions because the derivatives of a function and its inverse have a special relationship. So let's have a little pre-cal review. To find the inverse of a function, write the function in terms of x and y, switch the x and y, solve for the y. This is your new inverse, which gets that notation if it is in fact a function. And let us remember that f inverse of f is the same as f of f inverse is x. If we are, again, as a function here for our inverse. All inverse functions reflect across the y equals x line, so the point AB on f becomes BA on the inverse. So how do we verify that we have two functions which are inverses? We do a composite substitution. So f of g of x, so g of x goes into f. F says 3 minus 4 times something, so 3 minus 4 times g. Do the work, you get x. And g of f of x should give us the same result. G says 3 minus something divided by 4. So 3 minus f divided by 4, do the algebra, and we get x. So that has verified that these two functions are inverses of each other. Find the inverse of a function, then graph f and its inverse. So here is our y equals 3 times the 5th root of 2x minus 1. Switch the x and the y and go through the process to solve for the y. And this is our inverse. Now, in green on my graph is our function. Okay. Notice when x is 0, y is negative 3. When x is 1, y is 3. And in purple is my inverse. And notice 0, -3 becomes -3, 0. 1, 3 becomes 3, 1. Notice that F is increasing, and so will F inverse. Notice where F is concave up, the inverse is concave down. Where F is concave down, its inverse is concave up. That's interesting. A function has an inverse. That is a function. If and only if it is 1 to 1. That means it passes the horizontal line test. So determine if g of x is 1 to 1. Well, g of x looks like this. No, it is not 1 to 1. It fails the horizontal line test. Therefore, we cannot use this notation. This notation is reserved for a graph which is actually a function. Now, if I restricted the domain on g to 0 to infinity, its inverse would be a function, and I could use this notation. So now this theorem becomes more important. A function is strictly monotonic if it is either increasing on its entire domain, in other words, show that f prime is positive for all values of x, or decreasing on its entire domain, in other words, show f prime is negative. This means there's no change in direction of the function, which makes it 1 to 1. Theorem, a function which is strictly monotonic on its entire domain is 1 to 1, and it possesses an inverse. We might add, that is a function. There's going to be one case where the inverse would not be a function, and that would be where we have our function, which is a horizontal line, and its inverse would be a vertical line, and that is not a function. If a function is not 1 to 1 on its entire domain, you can then restrict the domain to an interval that is strictly monotonic. For instance, let's look at the sine function. We know the sine function is not 1 to 1, but if we restrict it from, say, negative pi over 2 to pi over 2, every value for sine occurs in that interval, and no value is duplicated. So that would make it 1 to 1 in that interval. And if I have that, I can then graph its inverse and think about its inverse as a function. Notice where sine is concave up, its inverse is concave down. Where sine is concave down, its inverse is concave up. But the sine function is increasing on that domain, and so is the inverse sine function. A theorem with obvious comments about it. If f of x is a function which possesses an inverse, if f is continuous on its domain, the inverse is. If f is increasing on its domain, the inverse is. If f is decreasing on its domain, the inverse is. If f is differentiable at c and f prime is not 0, then f inverse is differentiable at c. This would be why a horizontal line whose derivative is 0 would not have an inverse that is a function. The inverse would be a vertical line. And let's recall, c f of c on function f becomes f of c on the inverse. So let's consider a function f and its inverse f inverse. Let's let y equal f inverse. Now we know from our pre-cal properties that if y is f inverse, I can apply the function to both sides of the equation. That's going to give me f of y here, and f of f inverse is going to be x here. So I have x to be equal to f of y. Now let's find the derivative in this equation. The derivative with respect to x of x is 1. Nice and easy. This is going to require a chain rule because the derivative with respect to x of a function of y is f prime of y times the derivative of the inside. In other words, the derivative of the outside, f prime of y, times the derivative of the inside. And if we solve this for dy dx, we get dy dx to be 1 over f prime at y. Now this is a very powerful result. Let's think about what y is. Y was f inverse of x. So when I talk about the derivative with respect to x of f inverse, I'm saying that if I wanted to take the derivative, 1 over f prime of f inverse of x. So this is a very nice rule. The derivative of an inverse is 1 over f prime of that inverse, evaluated at x. Translation: the derivative of an inverse function is the reciprocal of the derivative of the function. Now we saw that in our very first example. So let's look at this one. So let's look at example 3. We're going to consider our function, which is an inverse, which is the square root of x. And we want to find the derivative of that inverse function. So if f inverse is square root of x, then f of x is x squared. Remember, if y is square root of x, switch the x and the y, square both sides, right? So if this is my inverse function, then this is what it was the inverse of. And we know how to find that derivative. So the derivative of my inverse, which is what this is asking for, is going to be 1 over f prime of f inverse. Now, f prime is 2 times something. Okay? F prime is 2 times something. So 1 over 2 times f inverse. What was f inverse? Square root of x. Now, if you took this and solved it, you can find that that derivative of square root of x is 1/2 x to the negative 1/2, which is 1 over 2 square root of x. But we need to know this formula. This is really important. The derivative on an inverse is 1 over f prime of that inverse. Let's consider y equals square root of x, find dy dx. Since y is square root of x, we know that x is y squared. So now I'm going to look at dx dy. The derivative of x with respect to y would give me 2y. Notice that's not a times y prime because it's the derivative with respect to y. And so if dx dy is 2y, then dy dx is the reciprocal of 2y, which was 1 over 2y. And my y is square root of x. Why do we need to know these theorems? Sometimes it's not very easy to find an inverse function. So these theorems allow us to find the slope of a tangent line on an inverse function without actually ever finding the inverse function itself. That's why this is powerful. Use the derivative to verify that the function has an inverse. Then find the derivative on the inverse at 7. Now let's remember, 7 on the inverse is the y-coordinate 7 on the function. Here's our function given to us. Okay? If I take this function and switch the x and the y and I get this, notice you cannot solve this easily for y. So this is going to be a case where knowing our theorem from above is going to be very helpful. So let us first find f prime, and f prime gives us this. Now we know what a parabola looks like. F prime is not 1 to 1, but that's not going to be important here. Since f prime is always positive for all x, except for when x is 2, f is increasing on its entire domain. Therefore, f inverse exists. See, that's the key. F is increasing on its entire domain. To find the inverse, we did that above. You cannot solve this for y, so now this is where we need to know this function. Okay? The derivative on the inverse at 7 is 1 over f prime of f inverse of 7. So I need to find on the inverse function when x is 7 what the y is, because the y on the inverse function is actually the x on our function. So f inverse at 7 also means f of x is 7. So this means our function would equal 7. Now that is actually difficult to solve, but we can try some plug and chugs, right? So let's start with 0. With 0, I get 0, and it's a miracle. With 1, I get 7. Yay! So if f inverse of 7 is 1, that means f of 1 is 7. Now we can find the derivative at 7 on our inverse. The derivative on our inverse at 7 is 1 over f prime of f inverse of 7. F inverse of 7 is 1. So 1 over f prime at 1. Well, f prime was way up here. 3x squared minus 12x plus 12. So substituting 1 gives us that. There we go. So f prime at 1 is 3. So the derivative on the inverse is 1/3. This results in the conclusion that the slope at x equals 7 on the inverse function is the reciprocal of the slope at x equals 1 on the function. Example 6. The function f of x equals k times 2 minus x squared minus x cubed is 1 to 1. And f inverse of 3 is negative 2, find k. If f inverse of 3 is negative 2, that means this equals 3. That means when x is 3 on the inverse, then y equals 3 on our function. When we have negative 2 for our x. So again, let's look at this. F inverse of 3 equals negative 2 means the point 3, negative 2 on F inverse, which means negative 2, 3 on F. Since this is F, I can substitute 3 here when X is negative 2 and solve for our K. Just a way to use inverse information. Examples 7, 8, and 9, I will leave to you to work on. Let's make a little change on 7C. Used to be you had to pay for long distance by the minute, so let's change it to parking in a paid parking lot, lasting T minutes. Let's change it to that. That's still relevant. And your TPs for this section are numbers 3, 5, 9 through 12, 23, 29, 71. See you next time.